Really, it's my pleasure to introduce today this dual presentation with really two long-standing collaborating and prominent GI scientists, Matt Duckham and Mike Worboys, who together really have made substantial contribution to the field of GI science over the past 30 years. The talk today is entitled Qualitative-geometric surrounds relation between disjoint regions. And this talk and this work can be considered, as it will be shown during the talk, as a contribution that follows almost 30 years of IJGIS publications that cover the field of qualitative spatial reasoning. Not mentioning that during the same period, Mike published with Matt a landmark book, GIS as a computing perspective. That book is still on my table, always not far away. And Matt, another one on decentralized spatial computing, foundation of geosensor network. So really, it's my great pleasure, as it is for us with May as IJGIS editors, to have Mike and Matt today. So without further ado, let us now welcome Mike and Matt. Really, the virtual room is yours. Matt, Mike,
thank you,
up to you now.
Thank you very much.
Thank you very much. Thank you for the lovely introduction, and thank you for the chance, May and Christoph, to come and talk about this paper. Yes, as you introduced, qualitative geometric surround relations between disjoint regions, and yeah, it's really lovely to be here and to be able to talk about this paper. Particularly, I certainly enormously enjoyed being involved with it and helping write it. So hopefully, I can do a good job of also communicating some of that enjoyment, to the people here and the people watching later on. But I do also want to start just by acknowledging Mike and Mike's specific contribution. So this is, we were looking back, and this is Mike's 13th paper in IJGIS, and that's, as Christoph was saying, one of, just one outlet of many where Mike's made a really, a superb contribution to the field. I'm very grateful personally for, being able to work with him and to, be a little part of that contribution. But kind of looking through those 13 papers, and indeed some of the other, contributions in other places. I think for me, the hallmark, Mike, of your work is really all about the sort of clarity and precision that comes when I read kind of your papers. And I know particularly those earlier ones when I was doing my PhD, and probably many people here as well kind of read those papers, and that really, they're foundational papers. And I think many of the things, when we do go a little bit off the rails in GI science, often it's because, and in other fields as well, often it's because we're not being completely clear with each other what it is we mean and what it is we're talking about. And I think when I look through those kind of your papers, every single one has that clarity and precision throughout. So wow. I'm saying all this, not because you're no longer active. You are very active, and but you've moved activity into a new area. So I know that you're now a recognized composer and no longer particularly working in GIS. So this, I'm guessing this is going to be kind of the last paper in IJGIS because you're off doing other things.
Well, thanks very much, Matt. I mean, yeah, I've been around a long time now. I still have a PhD student in GIS, so and also some master's projects. So I'm not completely out of it, but it is true that I'm spending more of my time in music these days. And since we're having this love fest at the moment, let me also also say what a great collaborator you've been over the years. I mean, with that first paper in 2005, but we went before that. So I certainly valued us working together. It's been a great collaboration. Anyway, we should get on.
Cool.
We mustn't.
Well, we'll get on with the paper then. Cool.
Yeah.
Okay. So this paper is all about surrounds relations, and in particular, higher order surrounds relations. So this was one of our motivating examples. Islands in the Gulf of Bothnia, close to the coast of Finland, and questions like, well, which islands surround which other islands? Were some of the motivating starting points for this. Now, of course, there is a little bit of a relationship here to regions within other regions, what are sometimes called, this idea of recursive islands and lakes. That's the Wikipedia page on that. I'm not sure it's the right term, but you can find all sorts of examples of in geography of where an island is completely enclosed within a lake in another island, and that might be in another lake. And in fact, there's there is one place I got from this page that has an island in a lake, on an island, in a lake, on an island, in a lake. So that really you can find examples of high levels of nesting of these sorts of configurations. But we're really interested in surrounds where it's not completely enclosed. And so our examples come from the Gulf of Bothnia. So this is in Northern Europe, and you can see the Gulf there. And of course, it's not completely enclosed because there's passage right the way from the North Sea into the Gulf of Bothnia. But it still, in some sense, is surrounded by Sweden and Finland. And if we zoom in a little bit, there's all sorts of, actually thousands of islands. I think over 200,000 islands in the Gulf. And so we can imagine, as we move through on this little boat, we're moving through this on a voyage around the Gulf, and our relationship to all of these different islands is changing, or as we move. And in fact, as we come round to this island of Replot, there's quite a big change that's happened here, where now we're somehow surrounded by just the two bigger islands, Replot and the one to the north, and even we might get almost completely surrounded by just one island here. But the key thing to notice in all of these examples is nothing has changed topologically. All of the islands, the boat, as long as it doesn't run aground, are disjoint, can be thought of as disjoint regions, and all, so all of the changes can't be described purely topologically. And so here the boats come to moor in a little bay inside an island, which happens to be also inside the Bay of Replot, which is, of course, in the Gulf of Bothnia area itself, enclosed to some extent, partially enclosed by Sweden and Finland. So these sorts of questions have been looked at in terms of how do we actually define the relationships going on there. Well, I've mentioned completely enclosed. We saw with the islands in lakes, in islands, and so on. There are a number of other definitions of this sort of partial enclosure that you can find in the literature. One in computational geometry is about kind of line of sight, the field of view. So here, if I imagine being on this orange region, then the angle formed by this field of view to the exterior is in some way a measure of how enclosed the orange region is. Another version is visually surrounded, where there's no line of sight out to the exterior, but there might still be a path that means that I don't have to cross the blue region. So that's another type of sort of partial enclosure. Another one used quite a lot in GI science is contained in the convex hull. So that also is another sort of form of partial enclosure. The the problem with all of those, or one problem with all of those, is that they only deal with individual regions, so one partially enclosing region. And so to deal with that, there's also a number of people in GI science have used the contained within the convex hull of the union of a number of regions. And so that's an example here that takes us beyond just two regions. But there's a couple of difficulties with that approach. One is that sometimes the results don't always look quite as we might expect, from a natural language point of view. This example, I think, might be more often classified as something like between rather than surrounded by. And also, it's difficult to know which of the regions to take in that union. If you think about the example of our ship moving through the Gulf of Bothnia, well, which islands do we take as our islands, to form the convex hull of the union of? So the approach that we use in order to capture this idea of surrounds is the region Voronoi diagram, which will be, I think, pretty familiar to most people. But if you're not, I'm guessing most people are definitely familiar with the point Voronoi diagram, which is where we partition the space into these Voronoi regions, where each Voronoi region is generated by a point. And so the Voronoi region is the set of points that is nearer to the generator than any other point. And exactly the same idea is behind the region Voronoi. So here we've got this orange region, and these points in this Voronoi region are closer to the orange regions than any other of those regions. We've used this in a paper recently in Transactions on Spatial Algorithms and Systems, where we also did a little bit of work on surrounds. And it's closest in spirit also to some work by Matt Doob and Max Eigenhofer on the surrounds attach relation, which is closely related, but uses space filling regions where there is no space between the regions where they actually abut. But here we've got regions, disjoint regions that have space between them. So we're going to see a little bit more of these region Voronoi diagrams. And just to mention one other point about higher order n-array relations, that we do need to consider the set of these, the relationship between the region of interest and a set of regions. And that will be potentially different from considering the pairs of regions one by one. So if you look on the this right-hand side, and then the configuration on the left, the relationship between the pairwise relationship, the binary relation between the orange region and each of the blue regions is unchanged. So if we only look at the binary relations, we're never going to get a very good picture of what's actually going on here. But as Lewis and Matt Doob and Max Eigenhofer kind of argue, I think, very well in a couple of their papers about these ensemble regions, we need to look at the set of all of those regions in order to be able to see, well, actually here, this orange region is really, completely enclosed by this ensemble of blue regions, whereas here it's outside. Okay, so how did we go about it? Well, the work's really founded on map trees. And map trees is work by Mike reported in 2012 and 2013 in these papers. And I think it's really, to me, a sort of missing link in some of the foundations for, spatial data and for GIS. It starts with the combinatorial map. This will be a structure that's familiar, I think, to anybody who's looked at computational geometry, and indeed it underpins a number of our basic data structures like winged edge and the node arc area model. And so the combinatorial map is essentially a graph. It's actually a multi-graph because we can have two edges between, or multiple edges between pairs of nodes. And it's a graph with an embedding. So it's actually embedded, in this case, just on the plane. And so when that embedding leaves us with these faces that are homeomorphic to a disk, then we have what's called a two-cell embedding, and that's our combinatorial map. So this might be, you know, let's say 4 regions separated by a number of boundaries. Now the limitation, why I say that there's kind of the map trees fill a gap in our sort of fundamental spatial data structures, is that combinatorial maps are very useful, but only deal with connected graphs where we've all of the vertices are reachable, or at least weakly connected, are potentially reachable from other vertices. But map trees deal with potentially unconnected combinatorial maps, sets of combinatorial maps, like this example here, where we've actually got 3 regions or 3 combinatorial maps that together tell us, you know, could partition the space. And what the map tree does is it gives us this structure to also capture these combined embeddings. So by adding in the adjacency tree here. So I'll just talk you through this because it's quite important just to really just see what this structure is doing. The map tree is composed of this tree with different colored nodes. We've got black and white nodes, and the black nodes relate to connected boundary components. So this black node here, for example, relates to this boundary component here, and the white nodes relate to faces in the structure. And then we label the edges between the faces and the boundaries with the actual cycles, the edges that give a cycle the faces. So let's see a particular example. Here we've got B overline C, and we just use the overline when, if you remember, we've got a directed multigraph. And so if we need to go in the opposite direction from the directed edge, then we've got a little overline. So B overline C here means we're going to go in the opposite direction to B and then in the direction of C. And as we go round, if you imagine walking round there, if you are on your left-hand side, you're going to find this face. And so that's what this is telling us here. Here, for example, we've got C overline D. So we're going to go in the opposite direction to C and D. And again, if you go around here and think what's on your left, that gives us this face. And then the third cycle here is B and D going in the direction of the arrows. And again, if you think what's on your left-hand side there, you'll find this face. And you can step through all of those different components there, and you'll see that actually this structure captures the fundamentals of the topology of these regions. Maybe now would be a good moment, Mike. I was just going to ask, well, first, hopefully I captured it relatively well, but when you were coming up with the map tree, what was some of the motivations behind that from your perspective?
Yes, I thought you did a good explanation of that, Matt. Well, I've always been interested in kind of these what I kind of call richer representations of space, in this case, two-dimensional space. In fact, I wrote a paper with Bavakis in 1993 for the IJGIS, where we're looking for these sorts of ideas. And I don't know, I've never been quite felt that some of the other formalisms really capture the whole thing, which includes both the topological structure of the regions, but also the way that these disjoint components, the way that they interact with each other. So the way that I came across the map tree was really from seeing that two ideas could be linked together. One was the idea of the combinatorial map, which you just described. But the other idea is the idea of an adjacency tree, which was developed by Buneman in a paper in Machine Intelligence, published in 1970. And that is all about disjoint regions, nothing to do with the topology, but just whether how regions are nested in each other. And that results in a tree. And I did some work with John Still on that, which was published in the Journal of Theoretical Science, which extended his ideas, Buneman's ideas. But I realized in about, I think 2009 or something, that if you put these two things together, you have a representation both of the complexity of the topology of the individual components, but also the way that they nest together. And that's really how the map tree arose. It's really a combination of these two different kind of structures.
Excuse me, microphone. Yes, great, and thanks. You know, that I think that combination is really powerful for a whole range of structures. And so what we're going to do in this paper, as you know, is talk about how we can use it to describe surrounds in a more precise way. But in fact, there's all sorts of potential applications, I think, for the map tree in general, just as there are for combinatorial map.
Because I just want to add one other thought, and that is that kind of the reason for doing this thing in the first place is it's really, I suppose it's about compression, really. It's to try and bring in as much qualitative information about the space, like, for example, surrounds, or into a kind of a formal description, in order that these formal descriptions can then be used for computational purposes as well as maybe inference and other things. So that's kind of really the sort of whole motivation for doing this. Yeah,
makes sense. And there's a question
Mike
there
and
from
Matt,
Lucy.
there is a question from Lucy. Sorry.
I'm just going to pick that up there. Yeah, so we need the question from Lucy is why is there both an A and an overline A? Why do we have both of those in the tree? And it's that we need to be able to describe all of the faces, we've got to be able to go round, traverse each region in using the edges in a different direction. So, for example, overline B is going that way around in the wrong, against the arrow, and C is going with the arrow, and that gives us this face here on the left-hand side, whereas BD overline without the overline gives us this face here. And similarly with A, we've got A going in this direction, and if you think what's on my left as I'm going around that direction, well, it's the exterior face, so this bit here. And then if you think, well, what's on my left when I'm going in the opposite direction against the arrow, it's going to be this region here, which is represented there.
Yeah, and it's because each edge acts as a boundary of two regions, one on each side, and we have to kind of distinguish which region we're dealing with.
Good question. Thanks, Lucy. Cool. Okay, so then using these map trees, we looked at, well, let's use them to represent the Voronoi regions, where we have where we want to be able to capture both the generators and the Voronoi regions that surround them. And to do this, Mike basically came up with an additional classification between the different nodes. We've now got not just black and white nodes, but in fact we've got nodes that represent the generator regions and nodes that represent the Voronoi region. So we've got them here, and I'll just give you them. So the I nodes are the interior of the generator regions. The B nodes, the boundaries of the generator regions. And then the VI nodes are going to be the interiors of the Voronoi regions, and the VB nodes are the interiors, the boundaries, excuse me, of the Voronoi regions. And then when we put all those together, actually there's already quite a lot of structure there, because the Voronoi, interior of the generator regions, well, they're going to be homeomorphic to a disk. We're going to make the restriction that we're not going to allow generator regions that have, you know, for example, holes or other topological complexities. So they're just going to be homeomorphic to a disk, and so they have just a single boundary, and so that's their boundary there. And then that boundary is going to be the generator, or that region, sorry, is going to be the generator for the Voronoi region interior. So we've got this structure here where that this node, each I node has to be of degree 1, each B node has to be of degree 2, and it's got to be connected to a VI node and to an I node. And then the Voronoi interior node must be adjacent to exactly one B node, but potentially could have a number of Voronoi boundary nodes that bound it essentially. But each Voronoi boundary node has to have a degree of at least 2. It's got to separate 2 things, and it's only going to be adjacent to these Voronoi interior nodes. It can't be adjacent to anything else. So we've already got quite a lot of structure there just by adding in that distinction between the Voronoi region related nodes and the generator region related nodes. And I'm going to mention one other thing at this point, and that is that because of this structure, because we always have a Voronoi interior node always has, if you like, a region generator boundary and a region generator interior hanging off it, we're going to group these together a little bit later, and we'll call them blocks. So just bear that in mind, and we'll come back to that in a minute. So now, what does this look like for our regions? In this case, we're going to start with regions on the sphere because it's simpler to describe the regions on the sphere, and then we'll come to the regions in the plane in a minute. But essentially, this is the simplest case where we've got 2 regions in a sphere. And a good way, if you maybe try and draw a mental picture for yourself, if you imagine a water world with only 2 continents or regions, if you like, an Arctic and an Antarctic, and so they're the only 2 regions. This will be R1 and R2 here, and they've got their boundaries. Then what you would imagine is, if you think of the Voronoi regions formed by those 2 regions, the Arctic and the Antarctic, well, they're essentially the 2 hemispheres. So these would be the 2 hemispheres, and then the boundary between those 2 hemispheres, the equator, that gives you the Voronoi boundary. So that's effectively kind of how to think of this diagram. That's what it's showing you. And the key thing is there is only one possibility here, and in the paper, that's something we show that there's only one possibility. This is the only configuration that's possible with 2 regions in the sphere.
You got a question there, Matt?
Oh, good. And so May's asking to have a boundary to generate an interior, so shouldn't a boundary node come before an interior node? May, is that question related to the order of them? Because they're not ordered. I'm just trying to interpret that question.
I think that's right. So I think there's no order there. It's just because one thing's to the left or right or to the top or bottom of another thing. That's kind of immaterial, really, if that's the point made.
No, actually go to the previous slide. And the I node have a lower degree than the B node. Does that imply that the I node have a lower order than the B node?
Not an
What do you mean by
order, so
what do you mean by order, May?
I would say like a lower order objects usually start first, or lower resolution objects start first. Then we can aggregate lower resolution to a higher resolution. So when I saw this graph, I would think that you imply that you have the interior node first, then you have boundary node, then you have a VI node. So as a like ordering, so that's not the case.
No, so maybe I kind of explained them in order, but they don't particularly come in an order, except that there is the generator region, and that region will have an interior and a boundary. And then there's the Voronoi region that is generated, by that generator region in building the Voronoi diagram. But they don't really have any order associated with them. And why? And there was a question from Christoph. Why so many VB nodes in the slide? Well, each Voronoi interior has to have at least one VB node that it's connected to. But actually, as we'll see a little bit later in some of the examples, it could have a number of VB nodes that it's connected to.
So is it possible to change the black and white fillings on the graph on the right? So we will have a black circle, then white circle, and then black square, and then 4 white squares. That can work, no?
No, because we have to have the interior the interior of the generator region has to be bounded by, has to have a boundary. So this has to be white and this has to be black. We couldn't just swap them round because it would violate these rules. And the rules are, but really describing what can actually happen with these sorts of regions.
So if you have a boundary node, like if you say that the black node is on the extreme right, that's a boundary node, and it's got to be a boundary of something, and so it's got to have an interior which is further to the right than it itself. So a black node can never be right as a leaf of a tree.
I see.
And perhaps now I'm just going to jump onto 2 regions in the plane. Maybe this will help make it a little bit more concrete for people. So in moving, we had them in the sphere, so we had the 2 poles and then the equator as the boundary, the Voronoi boundary between them. And when we move into the plane, we need to pick, a region. We need to pick. Essentially like. Pricking a balloon, we need to find a place to puncture this sphere, and then you can imagine sort of laying it out on a table, and if you can sort of picture that distortion in your mind, there's actually it makes a difference where you puncture the sphere. Now, we're not allowed to puncture it in a region or a generator region or a generator region boundary, because we're only allowed regions that are generator regions that are homeomorphic to a disk. But we can puncture it in one of the Voronoi regions or on the Voronoi region boundary. And these are the 2 options that come out of being able to do that. Here on the right, we imagine we've taken this sphere and we've punctured it. In this case, in the B1, in the Voronoi region interior. And so hopefully you can imagine doing that. You'd sort of prick it somewhere, perhaps near where the UK is, and then spread it out on the table. And if you did that, this is what you would get. You'd get this region R1. This is the interior of region R1. We've got the boundary of region R1 here. And then this is all within this Voronoi region of V1. But we've also got this Voronoi boundary here that separates the Voronoi region V2 that's closest to R2 from the Voronoi region V1 that's closest to R1. And so that's why we've got this sort of structure here. Now, we could also have punctured it at V2, but we would have ended up with exactly the same diagram, just with the labels changed. The other option is to puncture it actually on the Voronoi boundary. And then we get this configuration where we've just got the Voronoi boundary here, and then the two regions are sitting side by side there. And they're the only two options. And again, that's something that's shown in the paper. There's no other possibilities for what can happen there. So hopefully that helps see a little bit more more concretely how these different nodes relate to these different structures.
You have another question, Matt.
Thank you. How to define the exact boundary of W? I'm not sure what the question is about, Myung-So. You mean how do we? I'm not sure what you mean by exact boundary of W. Maybe we'll come back to that one.
I think one of the things here is that that's what you'd have to define a Voronoi region, but or a Voronoi boundary, I should say. But exactly where that boundary is, it doesn't really matter. It's more the topology of the boundary that's important. So if you don't quite get it exactly right geometrically, that doesn't really make any difference. As long as you have the topology correct, then everything else will follow.
I hope that answered your question. And then, well, I'm just going to quickly mention the three regions on the sphere. And again, you can do this perhaps in your head. If you imagine we had our two, the Arctic and the Antarctic, and the two hemispheres with the two Voronoi regions, and then the equator was the boundary between those two Voronoi regions. If we now introduce a third region, let's say Trinidad, somewhere near the equator, then what you can imagine is, well, then there'll be a new Voronoi region that will surround that generator region, the Trinidad as the generator region. And in fact, what the map tree will look like is this one here, case B here. So we'll have a rather more complex Voronoi boundary that actually connects to three Voronoi regions, and then to each of the three generator regions shown with the combination of the generator region interior and generator region boundary. And then the other option is, if you imagine towing Trinidad all the way north, we'll head towards the Arctic. At some point, the Voronoi region for Trinidad may actually become disconnected from the Voronoi region for the Antarctic. If we get close enough, and perhaps Trinidad actually ends up in a bay in the Arctic, and that's the situation here. So in that case, these two nodes would be the Arctic, which would share a Voronoi boundary with both the Antarctic and Trinidad that's moved right up to the north, but these two, Trinidad and the Voronoi and the Antarctic, wouldn't share a Voronoi boundary.
So maybe I could just add something, Matt. Is that okay?
Yeah, please do. Yeah, please do.
If we were sort of thinking about the motivation for doing all this, so some of the earlier work was looking at it kind of top down in terms of the general abstract structures. But what we're doing here is we're trying to go bottom up. We're saying, how can we use this thing to find all the different ways that two regions can work in this situation, and then three regions. And so we're using the map trees to actually prove that there are only a finite number of configurations that can work, given that the constraints that we've got in terms of the Voronoi Voronoi diagram. And so that's really what's happening here. We're moving from 2 to 3 and seeing all the different possibilities that can arise. Hope that helps.
That's it. Yeah, no, that does. That's a very good way of putting it. So yeah, exploring all of these possibilities. The possibilities for 3 regions in the plane are also in the paper, but I'll leave those for people to look at, because they're a bit more, I think they just reward a little bit of sitting down and thinking about them and reading through them. But then in going both from 3 to 4 to 5 and so on to more of these regions altogether, we really then looked for a computational way of doing this. 2 and 3 Mike did by actually sitting down and proving them. But to really scale up to more regions, we wanted a way to be able to get a computer to do that, to actually exhaustively go through all of the possibilities. So I'll just try and very briefly indicate how we did that, but I'll skip through it quite quickly, conscious of time. In order to get a computer to look through all these possibilities, we needed a data structure that would essentially be searchable, where we could look at all the possibilities. And we did that by translating these map trees into an adjacency matrix. This is a standard data structure that people will know if you've programmed with graphs. It's a way of representing a graph as a matrix, and essentially you've got all of the nodes as rows and columns. And then in a simple bidirected unweighted graph, we just use 1s for all the node pairs that are connected, and 0s for all the node pairs that are not connected. And in fact, when we do this with the region map tree, to cut a long story short, we don't need the whole adjacency matrix. We just need one little corner of it. And basically this corner is all of the Voronoi interior nodes, so the nodes that represent Voronoi interiors, and then all of the Voronoi boundary nodes, the nodes that represent the Voronoi boundaries. And that gives us all of the information we need in order to describe the whole R map tree. And so here's a quick example. This is a region map tree, and here you notice we've just moved these nodes here that were VI nodes. We've changed them into these blocks where they actually, because if you remember, each VI node also has a region generator boundary and a region generator interior hanging off it. So we've just collapsed those into one node, as I mentioned, was going to happen. And then each of these region map tree adjacency submatrices, they all actually describe this structure. They're actually equivalent, but we wanted to have a single canonical form so that when we were doing searches across all of the possibilities of 1s and 0s, we had a single canonical form to be able to compare. And so essentially we've got a sort of greedy mechanism for deciding which of these different options we're going to use to actually describe this map tree in matrix form. And again, I'm going to skim on, conscious of time, but essentially this one is the canonical form, and we can always come up with a canonical form for region map trees. And then, just like we had a number of constraints for the region map trees, we can also translate those same constraints into constraints on the region map tree adjacency submatrix. And we need this because we need to be able to tell the machine what to look for, where it needs to look and where it doesn't need to look. Just comparing on the left-hand side the region map tree constraints and the region map tree adjacency submatrix constraints. The first two we don't need for the region map tree adjacency submatrix because they deal with I nodes and B nodes, which are anyway if you remember, they're part of the block, so they don't actually they don't affect the region map tree adjacency submatrix. These two constraints essentially translate directly to constraints in here on the right hand side on the region map tree adjacency submatrix, and these two constraints essentially encode that it has to be a tree. When you draw a tree with our diagrams, you can see immediately it's a tree. But when we do it in an adjacency submatrix, we have to just specify what those constraints are. And we can show that those are necessary. Again, I won't go into the detail here, but each one of those constraints is necessary, and we prove in the paper that that's the case, that we can, if we remove any one of those constraints, we can always find a counterexample that satisfies the other three constraints but isn't a map tree. And so then we let the computer go on that, and we actually generated all of the possibilities, not just for 2 and 3, but actually all the way up to 7 regions. So every possible configuration, only in the sphere in these cases, we didn't do the plane yet, but all of the possible configurations of up to 7 regions and their associated Voronoi regions. And so here's some examples, again, just to help you visualize it, of a region map tree with 5 regions. And so we've got our 5 regions that we can just distinguish here as M, I, K, E, and W. They're all homeomorphic to a disk. And so this is a realization of this R map tree, where we've got one Voronoi boundary. It's this whole connected component here. It goes all the way around the back and round the front again. And we've got these 5 regions here, all of which share a boundary with each other. This is the next one, where now we've got 2 Voronoi boundaries. We've got this component here, and then we've got this component that again goes all the way around the back. And it's E, it's this region here, which corresponds to this one here, that actually separates these 2. Skip over that one. So where did we all end up? Well, this does provide, coming back to the original motivation, this structure does provide a really precise way of answering questions like, which of these regions surrounds which other ones? And we get a very rich representation of the not just the topological relationships, but these geometric flavor to these relationships. So here we can say, because of this region Voronoi diagram, that this region I2, this island I2, is surrounded by the ensemble, by the combination of I1, I3, I4, and I6. Whereas I6 is one of the regions that surrounds I2, and in fact I2 is one of the regions that surrounds I6. But we need I2, I1, I7, and all of these regions together to surround I6. And all of that information is contained within the region map tree, where we can actually see and query this information. And in fact, we sort of talk a little bit about where this work is heading. If we now go back to this example of the ship sailing through the Gulf of Bothnia, actually, as this is happening, there's all sorts of changes going on. We've missed off, a lot of the different regions and the labels. So if we had that full complexity, we'd be able to see all sorts of other changes occurring, as that happens in these sort of configurations of, which regions, which islands are surrounding the boat. But in fact, there's also these quite significant changes in structure to the map tree as well. Here at this point where the boat's sort of crossing into this bay in the island of Replot, there's this moment where, so I'll just go back, the boat actually changes its position and becomes now, actually connected to a different node there in the map tree. And finally, when we go even further in, we'll find the same thing happens a little bit later, where we go right the way in to the island, and then there becomes a point where the structure of the map tree changes as well, not just the labels there.
You have a long questions, Matt, but you can finish and then come back to the question.
Cool. Well, I was really pretty much finished there. I was just going to say, future work to do, lots of it. We would like to do more, explore more than 7. It's quite computationally expensive to get up to these 7 regions. And thanks to Aussie Yagwang Tao for helping run that code. And yeah, all of these things like similarity of scenes, conceptual neighborhoods, and these events, what's happening to these evolving regions. And we can see lots of applications. We work, for example, with defense, and these are really important questions for intelligence. Just as a simple example, how do the how does this scene how similar is it to other scenarios that we've dealt with? Is this units surrounded by other units? These are all actually questions that have direct relevance to real applications. So thanks, Maddie, for the question. I'm just going to read through it. So the first question is to applying map trees to indoor spaces. Maybe that's one for you, Mike, because I know you've done a lot of work with indoor spaces. And
yes, Li-Ping was one of my PhD students when I was in Maine, and we did work on indoor spaces. Did consider using map trees, but most of the indoor spaces that we came across didn't really have this kind of disjoint nature. Mostly they're kind of connected spaces, so it's really a kind of the combinatorial map which is mostly at play there. So we didn't really pursue that direction. But if you had an indoor space where you had lots of islands within islands and so on, maybe offices within offices or desks, or I don't know, it's kind of difficult to really imagine the kind of applications there. So, but certainly an urban space would be more appropriate for that kind of treatment, I think. So we didn't really pursue that direction. I don't think Li-Ping herself, who's now at University of New Mexico, I don't think she's actually following that direction. In terms of 3D, well, I mean, in some ways it's kind of hard enough with 2D. We're worrying about 3D. And since I'm now at the end of my career, I'm going to have to leave that for younger and more intelligent people. I have to work on that kind of stuff, so I'm going to leave that one. The second part of the question, I think, is to do with storage. Maybe, Matt, you'd be the best person to answer that question about the database.
Yeah. So certainly you absolutely could store that in a graph database. I'm not sure you'd get much advantage from it because at the moment the actual map trees themselves are relatively small, although actually now I think of it, if we were actually to store all of the the 200,000 islands, that would be a much bigger map tree. So yeah, you certainly could store that in a graph database. You could also just store it because we're only really storing the same information associated with each node and each edge. Is also fairly straightforward just to store it in a matrix. Yeah, both are possible. And a question there from Christoph. I implicitly mentioned the relation between perception and language. Yes, when introducing some of the basic examples. To what degree do the different map tree configurations, especially for the moving ship example, might be connected to language expressions? Yeah, that's a good, really good question, Christoph. And we tried in the paper to steer away from, trying to be too definite on, how people use language, because I think people's use of language about surrounds actually varies quite a lot. And sometimes when we use surrounds in one circumstance, we might mean something a little bit different to how we use surrounds in another circumstance. So potentially all of those different models that I showed, precise models of what, how we could capture surrounds topologically or geometrically, they might all in different circumstances apply with those different linguistic configurations. But I certainly have the feeling that personally, my intuition is that the way that we've defined surrounds, well, it's mainly done that way because we really do have, I think, a clear picture of a precise definition, not just for a pair of regions, but for any number of regions. But it certainly also seems to accord quite well with the sort of my personal expectations of what it would mean linguistically. But we haven't tried to go into the sort of linguistics of surrounds, but I do think others have looked at that more.
It is possibly a way of disambiguating different uses of these kinds of terms like surrounds. So you could use these map trees to kind of give a formal description of one particular usage of the term or meaning of the term as opposed to another one. So it could be used for that purpose, but we haven't pursued that direction.
There may be also some language issue. Another question from Lucy, Matt and Mike.
Thanks, Lucy. Just doing some analysis on marine functional habitat connectivity, combination of a graph approach with friction surfaces, and whether a tree would help in pruning the analysis. We should talk more, Lucy. I suspect some of these tree, some of the data structures that already people are have used for describing and computing with kind of regions and how they relate to each other may well fit your needs there. So yeah, I'd be keen to chat more, Lucy.
Anyway, thanks, Mike and Matt. What I will suggest for the one that will listen the recorded seminar, there might be a chance to come back to either Mike and Matt by email. I don't really send too much emails to them, but I'm pretty sure they will come back to you for the one that will listen to the seminar later on, because it's quite early in the US for sure. Still a chance to have a last question from the audience. May, do you want to add a closing word? Yeah.
I actually have a question, if you don't mind.
No, please.
So you mentioned that each interior node will connect to a boundary and only one boundary, and also one Voronoi boundary and also one Voronoi boundary. But then when you give the example to identify surround islands, and it seems to me that the boundary of the interior space is no longer useful. We only need to identify Voronoi regions and Voronoi boundary to identify surround. So is it that the reason you say that we can collapse the interior nodes and boundary node?
Yes, yeah. So the really all of this later on works quite well just with the Voronoi boundaries and the Voronoi interiors, where necessarily the Voronoi interiors have to have a generator node and a generator region. So yes, we've collapsed that into a block, but actually all of the things that we were talking about before sort of do the structure, it really hangs off that relationship between the Voronoi interior and the Voronoi boundary.
Yes, and I could add, in this specific application, this specific paper here, it's really the Voronoi boundary, the topology of the Voronoi boundary that's really doing most of the work. But there could be many applications where the region itself and the topology of that is interesting as well. And in that case, we wouldn't be collapsing the bottom two nodes, but it just happens that we're really more interested in this case in just exploring, well, what happens if you have these very simple regions which essentially we treat as homeomorphic to the disk? How can they relate to each other in terms of a kind of generalized surround idea? Does that help at all?
Thank you. And also, and you mentioned that there are for the 6 regions, then you have multiple metrics to determine whether the relationship is valid or the metric is valid. But do we have to do that for every number of regions, or is there a computational rules can help us to expand from 6 regions to X number of regions?
You only have to do it if you want to know all of the possibilities. So that was what we were doing here, is really exhaustively checking, for example, for 7 regions, can we describe every possible configuration? But if you don't want to know that, you can still apply this structure. And some of the work I was sort of hinting at in terms of conceptual neighborhoods and events occurring, for example, with things moving around spaces, we can do that just with the region map tree structure, even if we don't know, well, this is one of 100 or 200 or however many possibilities with 20 regions, let's say. So does that answer your question?
Yeah. I'm just thinking about a lot of recent research look at the trajectories of movement patterns in the urban area when they go through different point of interest, for example. And so the adjacency submetrics may help us to understand that how different point of interest or urban features relate to that trajectory. And then to do semantic trajectory modeling will be quite useful with this method.
But the adjacency submatrix is just a convenient computational representation of the region map tree. So it's really the region map tree. But yes, we could use the adjacency submatrix and look at comparing different changes to those matrices.
Yes, but I also think that the adjacency submetrics, this just reminds me about Hamming's code, that they will be able to look at the matrix to see whether the message have errors or not. So we can look at the matrix to see that whether that trajectory is even possible, or.
That sort of thing would, absolutely,
Yes.
That's a good idea.
I just want to add a little bit about the history of this paper. You might be interested in that. I first of all wrote the paper in a rather different way to begin with, and I submitted to the IJGIS, and it was rejected because people thought, what the hell's going on here? This is too complicated. So then I had another go at trying to make it more simple, and I think I submitted it again, and I got it rejected again, I think. So I was more or less about to give it up, and I think I was talking to Matt, and so Matt said, no, we could do something with this. And I must say that Matt's done a tremendous job of actually making some of this clear. And Matt was actually responsible for all the computational work, all the matrix analysis and so on. That's all Matt. So in the end, it was a kind of a 50-50 collaboration. But it was interesting that it went through these two rejections. It may well never have got out into the light of day. And you might say, well, maybe it was a good thing that maybe it shouldn't have done it at all.
Yeah.
But you know, Mike, this is encouraging for the young fellows, and some of them are attending today. So even Mike can be rejected.
Yes, keep going, keep going, be persistent.
Yes. Well, I just want to thank Mike and Matt for this really insightful and very, I think it's really at a high level of geospatial information sciences. And then we need more research in this nature to really solicit the theoretical foundation for our disciplines. Really encourage people to get in touch with them and then to have more research in this nature and to really advance GI science. Beyond just applications and beyond just apply existing methods to the new data set, even though that's very important, but I think theoretical foundation really help us to go to the next level. So thank you very much for participating in this webinar, and thank you for all the very interesting questions raised by the participants. This is our very last webinar of this year. We might not continue next year because I think that a lot of people have webinar fatigue. But we may have, when we find that there are very important papers that get published in IJGIS, we might have some webinars that particularly for that paper. So Christopher, do you want to close this webinar?
Thank you very much, Matt and Mike, and really we look forward more seminars next year, May. Yes, thank you.